Hello. In lesson 3.2, exponential growth and decay, you'll learn to use exponential models to model functions to model and solve real-world problems. Let's begin by going over the difference between an exponential growth and exponential decay. An exponential growth occurs when a quantity exponentially increases over time, meaning that we're multiplying the same quantity over and over and over again over a period of time. That makes the function f of t equal to an initial amount a times 1 plus r, which is the growth, the rate of growth, 2 raised to the power of t, which is a length of time. The difference between an exponential growth and exponential decay is that for an exponential decay, the function rule would be f of t is equal to a times 1 minus r raised to the t power. So for a growth, you add the rate to 1, and for a decay, you subtract that rate from 1. And that value, this value here, is being multiplied a t amount of times to this value of a, and this value would be multiplied a t amount of times to this value a for the decay. So let's see how this works. So let's say that we have, again, that Brooke started her career with an annual salary of $32,000, and that each year thereafter, her salary is going to increase by 2.5%. So it's a rate of growth of 2.5%. And we want to figure out her salary after 30 years. So the function where we're going to use would be f of t is equal to 32,000, and we're going to multiply this rate of increase, which is 1 plus 2.5%, which is 2.5 out of 100, and we're going to raise it to the 30th power. So multiplying that is going to yield us our solution. So after 30 years, her salary will be $67,122.16. Let's look at another example of this similar situation. Now let's say a math teacher has 140 YouTube subscribers. The number of subscribers is going to increase by 4% each week. How many subscribers will she have after 2 months? Now, the one thing that needs to be consistent, again, is the unit of time. Since the rate of 4% is increasing on a weekly basis, after 2 months would have to be converted into weeks. And since there's 4 weeks in a month, that means that the time will be 8 weeks. So here, to figure out the number of subscribers this math teacher will have after 8 weeks, we'll start with the 140, and this 140 is going to increase by 4% every week. So we're going to multiply 1 plus 4%, which is 0.04 as a decimal, and we're going to multiply this number 1.04, 1 plus 0.04 or 1.04, 8 times to this 140. Which estimates to a total of 191.5, and because we're talking about people, subscribers, we're going to estimate that to 192 people. So after 8 weeks, this math teacher will have 192 subscribers to her YouTube channel. Now let's compare this to an exponential decay. For an exponential decay, we have here that Kate drank an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system is going to decrease by 12%. So how much caffeine is in her system after 8 hours? So our function will now subtract 1 by this 12%, which is 0.12 as a decimal. And we want to know, if I do this 8 times every hour for 8 hours, how much caffeine is going to end up being in her system. So we'll multiply 120 times 1 minus 0.12 raised to the 8th power, which is going to equal to approximately 53.95 milligrams. So there's your answer. So these functions, again, are not hard to use. You just simply have to input the corresponding values into the corresponding values into the function. So let's look at another example. Here, the half-life of Mercury 197 is 3 days. This is an interesting one because this is decreasing. Half-life means it's going to decrease by 50% every 3 days. So we're going to decrease 50% every 3 days. So we're not going to multiply the initial value A with 1 minus 50% 20 days, like in this example. We want to figure out the amount of Mercury 197 left from a 50-gram sample after 20 days. So we would think again of setting this up as 50 grams, and we're going to multiply this 50 grams with 1 minus 50%, which is 0.5 as a decimal notation. Or if you want to set this up in the following way, you can. 50% literally means 50 out of 100, so you could set it up like this as well. And instead of multiplying this amount to the 50 20 times, raising it to 20 times, because this is only occurring, it's only decreasing every 3 days, this 20 is going to be divided by 3. So it's really only happening around 6.66 times in those 20 times. That's how many times we're going to multiply that value. So let's see what this is going to end up equaling to. So after 20 days, half-life having a Mercury, the half-life of Mercury 197 is going to give us, with 50 grams, is going to give us approximately 0.49 grams. That's how much is left if the half-life, if it decreases by 50% every 3 days. There, I said it correctly finally there. So there's your answer. Let's look at some more examples, or let's look at a different model now. Now, in some functions, when a function is continuously increasing or decreasing at an exponential rate, and not just after every hour, month, day, etc., then we say that it has a different function, and the function is referred to as a continuous growth or continuous decay. This function is modeled by this equation. It uses, again, the value of P, which is the initial amount, R, and I misspelled initial. The initial amount, R, represents the rate of growth or decay, which will be positive if it's a positive rate of growth, and negative if it's a negative rate of growth or a decay. And T is going to be the time. And again, the time just has to match up again with the rate of increase or the rate of decrease. So like if the rate of increase is days, we want our time to also measure in days. So let's look at some examples of this. So let's say a garbage dumpster started with 4 pounds of garbage. The amount of garbage increases continuously by 35% each day. Let's find the amount of garbage in the dumpster after 2 weeks. So because it's continuous, we're going to use this function. And because it's increasing, this value of R is going to be positive. So starting off with the 4 pounds of garbage, we'll multiply that with E, raise it to the 35%, which is 35 out of 100, which is 0.35 as a decimal, and we're going to multiply it by 14 days, because since the rate is measured in days, 2 weeks has 14 days in it, so that's the number that we use, which equals to 537.16 pounds. So after 2 weeks, 14 days, that's how much garbage has been collected at this dumpster. Now, let's look at an example of continuous decay. Now, let's say the population of a town is continuously declining at a rate of 1.5% every month. If the current population is 16,000 people, what is the population after 8 years? Now, notice that the rate of decay is measured in months. So we want to convert our 8 years into months. And well, since there's 12 months in a year, multiplying that by 8, that's going to give us a total of 96 months. So our t will be 96. So our function f of t, because it's continuous, would be this. The difference though, however, is because it's decreasing, the rate of 1.5% is going to be negative. And 1.5%, which means 1.5 divided by 100, is equal to the decimal value of 0.015. So we're going to raise this to the negative 0.015 and multiply it by the 8 years, which in months is 96 months. Which is going to equal to approximately 3,791 people population. So these are the number of people left in this town. Now the last model we're going to go over is called the Logistic Growth model. This is a more realistic model for exponential growth because we do not have unlimited resources for things to grow again without bound. And an exponential function that increases and then levels out, approaching a horizontal asymptote, is referred to a logistic growth model. And the function below it is the representation of this model. The value that you need to know is simply this value of c. This is our ceiling or our cap. And this is represented by the ceiling of a function, which is going to be the maximum amount that the value can actually reach. And it's going to represent again as an asymptote, a horizontal asymptote in this model. So let's look at an example of how we use this. So let's say that there's a town of 20,000 people and that a disease begins to spread around this town. And let's say after t days, the number of people have been infected by this disease is modeled by this function shown below. Now, using this function, let's find the number of people infected after 10 days. Now, notice because there's 20,000 people, that is going to be the cap, the ceiling value in this function. The other two numbers, again, are going to be provided for you. So we don't have to worry about calculating those values of A and obviously the rate of 0.95. So let's look at how many people are going to be infected after 10 days. So we model this function f of t with 10. And we substitute in t with 10. So dividing this out, we get a total of 15 people. So we end up with 18,414.8, which we'll estimate to 15. So 18,415 people would be infected by this disease after 10 days according to this model. So there you have your answer. Well, that concludes again the examples on the various models and functions on exponential growth and exponential decay. If you have any questions, please do not hesitate to send me a message on Remind or through email. And again, I thank you for watching and I hope you have a great day.